Yeah, thanks. So now we'll have Mike's talk. Mike is awake since very early morning. And of course, Mike has worked on all areas of hot and dense QCD matter, especially on hard thermal loops. And there are so many exciting results he has on anisotropic hydrodynamics and also on charm and bottom quarks in heavy ion collisions, and of course plasma instabilities in anisotropic plasmas. So I learned a lot from his papers, and he has produced so many exciting works that I cannot summarize now, but he will talk about his new recent work on non-equilibrium attractor in high temperature QCD plasma.
Mike, please unmute yourself. You are muted. You have to unmute yourself first. Mike, please.
Yeah, sorry.
Okay.
Got it?
Yeah.
All right. Yeah. It hid the button from me for some reason. All right. Thanks to the organizers for inviting me and for organizing such an interesting meeting. I wouldn't have woken up at 4 a.m. for just any meeting. All right. So today I'm going to tell you specifically about a recent couple of papers, one from myself in 2018, and then most recently from my student Dekrayat Almalal and Alexei Kirkala and myself that appeared in PRL this year. So it's not going forward. All right, there it is. So this, in case you've never met Dekrayat in the age of virtual meetings, we don't get to see each other face to face. This is what she looks like, and this is what Alexei looked like many years ago. Now he looks more, let's say, rugged. All right, so as we all know here in this meeting, what we're trying to solve is related to experiment, right? So we have some heavy ion collisions, and they create some fleeting quark-gluon plasma in the experiments, and then we want to try to model that, right? And the standard go-to for modeling this has emerged to be hydrodynamics or viscous hydrodynamics in general. And what we do in viscous hydrodynamics is we take one of these initial overlaps, which is randomly generated from our nucleus-nucleus collision, and then we evolve it in time, and then we might, so going down here is evolving it in the time, and then we might ask what happens when we turn on the shear viscosity, that's the middle column, and maybe if we also had bulk viscosity, that's the next column. Now, of course, just looking at these pretty pictures, we can see that the effect of the shear viscosity in particular is to smooth out these sort of shockwave-like structures that we see in the ideal solution. At early times, the bulk has less effect, but if we go to late times, we'll see that the difference between the bulk and non-bulk starts to be important, and that's because the bulk effects tend to peak around the phase transition temperature. And here we can even more clearly see the difference between what happens, in the space-time dynamics from ideal hydroevolution and viscous. So viscosity just tends to blur everything out. Now, you run such simulations and then you extract some hypersurface, which is some 3D surface in a 4-dimensional space-time volume, and then you produce particles from this, and then you can compare to experimental results for, say, the spectrum of pions, kaons, protons in several different centrality classes. You can do the multiplicity, you can do the elliptic flow. And it's not just my group that does this. There are many groups. We're not even the standard bearer. I would say these days, there's many groups that can generate equivalent results. So in physics, we usually don't want to stop. When we see that something's working, the next question we want to ask is, well, why did it work? Did we just get lucky somehow? It's not good enough just to get something that happens to go through the data. So that brings us back to a discussion of, sort of how do we know if hydrodynamic modeling is reliable? And in general, we imagine that we can take the full energy momentum tensor of the system and split it into some ideal part plus some viscous stress tensor, in this case that includes both the shear and the bulk viscosities. And then the magnitude of this quantity, pi mu nu, tells us the difference from purely ideal hydrodynamics, right? So we can use the magnitude of the quantities in this tensor to measure our deviation from equilibrium. So there's two numbers. You can decompose this viscous stress tensor into a shear component and a bulk component, and from those you can define two inverse Reynolds numbers. The first is the inverse shear Reynolds number, which is just the full Lorentz contraction of the shear part of the viscous stress tensor, square root over P naught to make it dimensionless. So these would have been the corrections to the pressure, and that's why we here are scaling it by P naught. Similarly, there's an inverse Reynolds number that can be associated with the bulk in viscous corrections, and that's simply the magnitude of pi, since it's a scalar. So what I show you here are just some space-time diagrams, essentially, of a heavy ion collision. This was from a 3D simulation. I've taken the z is equal to 0 plane and then also y is equal to 0. So I'm just showing you the line along x here. This is the center of the collision here. And then going up here is going forward in time. And what's plotted on the left is the inverse shear Reynolds number, and on the right is the inverse bulk Reynolds number. Let's focus on the left first. So anything that has a lot of color here means that this number is big, and that means we have a sort of far from equilibrium situation on our hands. So if we look at early times, we see here in this diagram that we have a lot of green, but then eventually it starts going back towards the blue territory, which means lower inverse Reynolds number. The stuff here that's going on at early times in the center of the diagram, that's mostly driven by the strong longitudinal expansion of the plasma, causing the longitudinal pressure to become significantly different than the transverse pressure. And then as a function of time, that relaxes. In the wings over here, we see some more potentially scary stuff going on, and that's due to the fact that the system is very dilute out here, and probably not well approximated by hydro. It might be better to do kinetic theory out there, but in practice, you can still run the codes, and you're not too sensitive to what's going on out in those wings. To guide your eyes, I've drawn two hypersurfaces here, one at 200 MeV, which we extracted from this one, and one at 155 MeV. And typically it's this lower temperature that we use when we're converting the fluid into particles. And as you can see in this region, we're nice and well into the blue. So that gives us a sort of justification a priori for applying near equilibrium freeze out on this hypersurface, because the corrections are indeed getting small in the simulation. On the right, we see a similar pattern in the inverse bulk Reynolds number. We don't, because it's isotropic, you don't see the effect of the momentum in isotropy so strongly on it at early times, but instead what you see is that near the phase transition, where the bulk viscosity itself is expected to go up and have some sort of Lorentzian structure, if you like, near TC, that we start to get bulk effects here. But again, if we evolve, and in this case, we put that peak in the simulation at 200, so you can sort of see the impact of that peak. If you put that peak lower, more towards TC, then you can start to have problems where the largeness of the bulk viscosity on the freeze-out surface starts to have effects on your results. In this case, we kept those, for the visualization purposes, well separated by just putting this by hand at around 200 MeV. But once again, and even here, it's even darker blue, so you're okay. Now, in heavy ions, we have, in the last 10 years, people started discussing, well, can we also generate quark-gluon plasma in collisions of small systems? So some proton on a lead, or maybe even proton-proton collisions. And if we look in certain subclass of events, which have very, very high multiplicity, we might see some signatures of the quark-gluon plasma. And there are indications that, that hydro puts curves near the data, let's say, right? But then you go and you play this exercise again. Well, should I trust the calculation that I just ran? And for that, you can make a similar plot. This is actually not the Reynolds number, it's the inverse Reynolds number, it's the Knudsen number, but this is what drives the inverse Knudsen number to be large in the end. And in this simulation, they put in a temperature-dependent shear viscosity, as shown up here in the upper right-hand corner. And then, like in the previous one, they show you three different freeze-out hypersurfaces here with 180, 140, and 100. And basically, in Niemi and Denicol's version of this graph, anything that's red is bad. So I put, to guide your emotions, a little cryy face here. And as we can see, even if we're doing freeze out out here, we might be worried that the corrections to perfect thermal equilibrium are large, and we should be careful. Now, this is primarily driven by the fact that the lifetime of these events is so small and the gradients are so large. The system simply is sort of in this region in time where you may have not completely equilibrated or even gotten close to being on the end of this hydrodynamic attractor. So you can ask, well, you can show me these pretty pictures, but does it actually affect real simulations? And for that, I point to a paper by Montessori, Schenke, Shen, and Tribetti, which came out in 2017, in which they looked at PLED using IP plasma plus music plus URQMD. And if you look in the paper, what they'll, they tried to say how big were these corrections that we get to perfect thermal distribution functions, which in this language are called delta F. And what they found was that as you go up in PT, you see more and more cells that have a delta F, which is actually bigger than the leading order term. And not only can the magnitude be bigger, which is this absolute value here, you can even find regions where the magnitude is bigger and delta F is negative. So that means in this picture that the total distribution function, F plus delta F, will have gone negative. So in their paper, they showed us some plots like this, which is the probability distribution function for this delta F over F. And I've tried to color in anything that's red as a potential problem. So here is something where delta F over F actually got bigger than 1, and here is where it got bigger or less than -1, and hence we have a positivity violation. So in practice, people deal with this in a sort of engineering way to try to cut off these regions where things get really bad, or by or implementing some methods, such as what's called the exponentiation method, to make sure that F itself remains at least positive definite when you're doing this switching. Now, if I were to show you a similar plot in lead-lead, it will also have these tails, of course, but the statement would be that the part between -1 and 1 here is completely dominating what's going on out here in the tails. So one of the practical goals for what I'm going to present in the rest of the talk is to try to address how can we fix this? Now, traditionally, going back to this slide, remember that we always think in this linearization way that we're near equilibrium, and we have some FEQ plus delta F. If we're not equilibrium, of course, you might want to go to higher order in this expansion in gradients to have a better description on the freeze-out hypersurface. But is there a way to test what prescription that you use at freeze-out against something QCD based? And beyond that, if we have an understanding of how to do this freeze out better at any moment in time, can we then construct hydrodynamic frameworks that more accurately describe QGP thermalization and apply them to phenomenology? Now, of course, the tool that I'm going to use today, well, not of course, but the tool I'm going to use today is effective kinetic theory. And Soren gave us a very nice introduction this morning to that. Now, of course, you could say, well, why not just get rid of hydro and then just use effective kinetic theory everywhere? It's much harder if in practice numerically to do that. And also A, and B, you don't know how to change the degrees of freedom when you go through the phase transition. So at least in hydro, you can implement this sort of based off of 3D kinetic theory, and then you can extend this across the phase boundary using a realistic equation of state. Now, the numerical complexity issues may go away as a function of time because computers get better every year, but I don't know a solution yet to how you switch degrees of freedom in the kinetic theory approach. And the main question I want to address today is, as we've seen in the morning talks, there seems to be a kind of hydrodynamic attractor that emerges. And traditionally, this was looked for by looking at basically the ratio of longitudinal to transverse pressure or longitudinal pressure to energy density. This is just one moment of the distribution function. And I want to ask the question, is there an attractor for the whole one particle distribution function? And if I know the answer for the whole one particle distribution function, can I use that as a practical sort of test to sort of gauge which freeze out prescription is actually the best one to use? So today I'll present some progress towards these goals. So to begin, I'll just do a flash review of this non-equilibrium attractor business to get our terminology on the same page. All right, so I don't want to do it from an incredibly formal point of view. What I want to show is just practically, how does it work? So what's shown here is a Bjorken invariant expansion. This is an exact solution of the RTA shown here. And this is the pressure ratio as a function of proper time for a given value of E over S. The top is 0.2 and the bottom is 1. Both with the same initial temperatures. Now we can put both of those on the same plot, which is shown here in the upper right-hand corner. And as we can see, there's a sort of universal behavior. All of these guys sort of land here together at late times, irrespective of how we initialized the initial pressure anisotropy, and likewise for the larger value of E over S. But then the magic happens is if we take this horizontal axis and not write it in terms of time, but rescale it by the relaxation time in the system. So that's what's shown. That's the same two plots as before, but now I've rescaled the horizontal axis by just dividing by the time-dependent relaxation time of the system. And as we saw in Soren's talk this morning, and also in Xiaojian's talk, you can express tau EQ. In this case, it was RTA is simply tau over 5 eta bar. This turns out to be just the inverse Knudsen number for the system. So this is inverse Knudsen number. So large Knudsen number over here, small Knudsen number over there. And as was pointed out this morning, what we see here is a certain loss of memory about the initial condition after about whatever 2 is on this scale. What the initial condition was doesn't matter anymore, at least for this observable. Now, to put timescales on this, I made this slide where you have what are the approximate timescales if this was an LHC heavy ion collision. And what we can see from this graph is all the numerical solutions, which are the dotted gray lines. They're flowing into this thing, which we now call the attractor. And there are various ways to extract what this attractor line is. We had one described to us this morning, but some of those are a point of contention. But for this particular case, which is RTA, it's perfectly well defined. The other line that's on here is first order hydro. So this is Navier-Stokes hydro. And as you can see at late times, irrespective of the initial condition, they all flow right onto this late time hydrodynamic attractor. So the exciting thing for many people when they started to see these attractor plots was that although it's nice that it goes on to first order hydro, and as I'll show you later, if you do second order hydro, you can push it back a little bit further. But even at early times, you can identify this thing. In this case, I varied the anisotropies, but there's another possibility, which is to vary the initialization time by just pulling what's called a pullback operation. You just take a fixed anisotropy and then start it in earlier times, and then you can build up this curve. Now, by the time the green and the black curves are all merged together fully, that's about 5 Fermi/c. So this would, functionally tell me, if I was using this as my approximation, that after 5, you can really trust hydro, and that means that heavy ions are probably okay. But for the lead-lead collisions, we're still in this time scale up to 5, the question is then, can we use the existence of this black line in a given theory and information about it to constrain the early time dynamics better, the early time non-equilibrium dynamics? As was also mentioned this morning, what's going on over here in this part of the graph is non-universal, in the sense that if I didn't show you RTA, which is what's on this slide, if I showed you Yang-Mills, it would look slightly different. If I showed you some strong coupling calculation from ADS, you'd get something else different. But once we get into this late time regime over here, it's universal. And all curves will fall on top of one another as long as you've properly adjusted their transport coefficients properly. So that means you tune G in the proper way in QCD so that you have a given shear viscosity in your code, and then you match it to hydro with that same viscosity at late times. If you do that procedure, these things are always guaranteed to overlap at late times. And as I've indicated here, although you might fall onto this Navier-Stokes solution at roughly 3.5, the question is how far can we push back this universal curve to earlier and earlier times. The other way in which these attractor curves are useful is to assess different hydrodynamic schemes. So here's a plot from a paper with George Noronha and Gabriel Dynamical. Here we plot it in terms of a variable called phi. It's like the PL over PT ratio upside down. This is free streaming is 3/4, and I believe 2/3 in terms of this phi function is the ideal hydrodynamic limit. The black line is the dotted dashed orange line is the exact solution that I was showing you on the previous slide. And then we can check how well does Navier-Stokes do, how well does Mueller-Israel-Stewart do, how well does the full second order theory from Dynamical, Niemi, Molnar, and RHIC do, and then finally, how well does a hydro do? So in this case, we see that all schemes eventually have their attractors going above 3/4, even for RTA. And what that means in practice is that whenever they go above 3/4, then the pressure just went negative. In a hydro, this can never happen because we enforce that the pressures are positive definite, and therefore we get the rate free streaming limit out. Now, the reason that a hydro does so well in this context is because normal viscous hydro relies upon a dual expansion in Knudsen number and inverse Reynolds number. And in a hydro, we throw one of those expansions out. We no longer truncate the expansion in inverse Reynolds number. In fact, we resum it to all orders in the inverse Reynolds number, which is functionally speaking this anisotropy parameter C here, if you like. So that's the reason that once you get down into this region with super large gradients that we're able to automatically satisfy this bound. All right, so this was the story as of, I guess, 2017. We had various theories. This was non-universal down here. People can extract attractors, and people were looking at various toy models. And I had the question at the time of, well, why not just look at PL over PT? We can look at any moment of the distribution function, and do we see similar behavior in the sense that we have a loss of memory of the initial conditions and convergence to a kind of universal curve? So that was my question here. Can we go beyond hydrodynamics? So normally, as I said, the hydrodynamic attractor business is confined to a discussion of the energy momentum tensor itself. And in kinetic energy, of course, that energy momentum tensor can be obtained from some Lorentz invariant integral over p mu p nu times the distribution function. What about more general moments of P? So what if, of F rather, if I put more powers of P here, do I expect to see attractors also in those moments? And the answer is not obvious a priori, because in any theory, for example, QCD, you might expect that the high momentum parts are relaxing more slowly than the low momentum parts of the theory. And so you might not see this sort of universal behavior emerging in higher order moments. So the question was, well, is it there? And to begin with, what I wanted to look at was a simpler theory. But first, let me just set up what I'm going to look at. So I'm going to show you lots of plots of what are called moments of the distribution function. We're going to work in a conformal 0 plus 1D transversely homogeneous case. Most importantly, conformal, and in that case, you can express all moments of the distribution function as some power of the energy to the power 2m, and for distributions that are even under pz goes to minus pz, some power of pz to the power 2m. You could also imagine that there's transverse momentum in here, but in the conformal system, you can always rewrite the transverse momentum in terms of the energy and the longitudinal momentum. So this turns out to be the only beast that you really need to consider. Now, some of these we know, for example, M20 is just energy squared times the invariant phase space measure times F. That's nothing but T00 in the local reference frame. And M01, well, that's nothing but TZZ in the local reference frame. For some of these we know, but the higher order ones, they don't have names necessarily. To address this question of how the higher moments behave, I'm going to start with a toy model, and the toy model is going to be relaxation time approximation. I'm going to start with this because I can solve it exactly in this case. So in a few papers back in 2013-14, together with Wojtek Florkowski and Radek Wróblewski, we showed that, and this was based on some much earlier work from Boehm back in 1984. We showed that you can write down the exact solution, in this case for the one particle distribution function, and then once you have this exact solution for F formally, you can evaluate any moment you like. So that's going to be our workhorse, is just that in the next few slides is just this analytic solution. And it tells us how to take some initial distribution function and then evolve it in time. That's the left-hand side over here. Now, what I'll show you next, skipping over how do you actually solve it, you can turn it into an integral equation, one-dimensional integral equation, and then extract the effective temperature, and from that you can construct any moment that you need. And now we're going to make plots of the attractor in this case. And in all of the panels I'm going to show you, I'm going to plot these moments scaled by their equilibrium value. So what's in the denominator down here is M01 equilibrium, which is that I assume it's in perfect equilibrium with the effective temperature that it currently has. And as before, I vary the initial longitudinal pressure around, and I find that it collapses onto this line. So this is what we we had seen before, that we have an attractor for the longitudinal pressure. You can then enlarge the panels and now look at all possible moments of the one particle distribution function. Let's start down here with the most trivial one. It's flat. That's great. That just means that energy is conserved in the system exactly. This one corresponds to something that would be like the screening mass in the plasma. And this is the number density, scaled number density. And as we notice, again, varying the initial conditions. In this case, I was just varying the initial longitudinal pressure around. You see that all of these moments collapse. And in fact, if you look carefully in RTA, you'll see that the higher moments actually collapse faster than the lower moments, which is a bit paradoxical, but it's RTA. So what this is suggestive of course, if you can extract this, is you start to believe that, well, if this subset that I'm looking at right now all converge, maybe all of the moments of the thing converge. And it's true. So I made even bigger tables than this, and I never found one that didn't in the RTA case. And so it suggests that there's an attractor for the distribution function itself. And so you can do that. So once I've done one of these solutions, I can go back once I know the effective temperature and reconstruct the one particle distribution function using this original analytic formula here, this integral differential, well, in this case, just the integral equation. And that's what's shown here on this slide. If I follow those solutions right along the attractor. So what that means is I give it an initial condition that's right on the attractor. Then this is what the reconstructed one particle distribution function looks like. We see two components of this. One is an incredibly compressed thing, which is really a delta function at PZ is equal to 0. That is the free streaming contribution to this attractor solution. And the little blob that's around it, that's the equilibrating part of the matter. These free streaming guys are essentially the population of particles that have undergone 0 scatterings. And so they're just free streaming and their longitudinal pressure is going to 0. But their population goes down as a function of time because they eventually do scatter. And so you start to see it diluting and eventually approaching this thermal equilibrium result. It does not quite there yet. You can still see a little distortion here. Now I can compare that to what would happen if I ran this exact solution for the one particle distribution function, which some just made up initial condition. I just distorted it as an ellipsoid, and then I let it evolve. And as we can see, as a function of time, these two things are starting to look more and more like one another. And in the paper, I provided a lot more measures of how this looks in practice and quantitative measurements for how these things approach one another. So with this, we've sort of, and more so, I would say, with this panel of slides, we've established in RTA, which is a toy model, that there is a kind of attractor that goes beyond these usual hydrodynamic moments and includes also higher moments of the one particle distribution function. The other thing I told you is that you can use knowledge of this attractor to then assess different hydrodynamic prescriptions. And I did that in the context of M01, essentially for you before. Now you can make tables of these comparisons. Here was our old comparison between the exact solution and A hydro, which is, in this case, is luckily right on top of it. This is second order viscous hydro. This is first order viscous hydro. And then we can move down to the right. We would eventually expect the hydrodynamic treatments to fail. And we do see that these moments, which in RTA are strictly positive, eventually do go negative. And at least for these moments, they're not well approximated by this viscous hydro form. Now, how did I get this panel? Well, what I did was I made the solution for the pressure here, and that gave me the shear viscous correction. And from there, I just used quadratic freeze out, like is applied in heavy ion collisions, to extract the curves in all other panels. From these, we once again see that A hydro does the best. It's not perfect. It's certainly missing some part of the attractor here, but at least it in this framework, they're always positive definite. So because of that constraint, you're kind of always closer to the curve. So of course, the question that we had after that was, well, does this exist in QCD, right? RTA is nice. You can solve that integral equation on a small computer, but let's try to go to the target theory. So for that, what we used was a numerical implementation of pure glue, Arnold-Moore-Yaffe effective kinetic theory. Soren gave us a brief introduction this morning. This includes elastic gluon scattering and also inelastic gluon splitting and recombination with LPM suppression encoded. And as I said, it goes both ways, but there's detailed balance. So in practice, we got lucky. We didn't really have to make too many modifications to the original curricular shoe code where they used to get the results for the pressures. We had to make it a little bit faster because we needed large lattices, but mostly it was just hooking up some new output for observables. In practice, we used a grid because this thing solves it in momentum space, and there's some momentum space grid which you use to describe the one particle distribution function. And in practice, we ended up using 250 points in the length of momentum direction, 2,000 points in the polar angle in momentum space, and just one grid point because it was boosted transversely homogeneous, so we didn't need any things going on in the phi direction. The reason that we needed so many points here was because we wanted to look at extremely high order moments where there'd be high powers of say, cosine theta hiding in the integrand. And so we needed a lot of points in order to discretize that the angular dependence of those functions properly. So as a result of having to jump to 2000, we then had to use some supercomputer to do the calculation. So comparing on the left bottom, this is the result that I showed you for our RTA for this scaled M01. This is the result that you see from EKT QCD for the scaled M01. Now there's a bunch of different lines here. They're initializing with different pressure anisotropies. And then the dotted lines here are with what we called Romachka-Strickland initial conditions. It's just a ellipsoidally deformed thermal distribution. And the other possibility we looked at were these over-occupied like CGC initial conditions, and those are the solid dashed lines. And we see that although at early times there is some dependence on the specific initial condition, we see that after some amount of time this all goes away, and they all seem to collapse to some attractor line. And then at a later time are described by first order gradient approximation. So again, just to assign some time scales, because I changed the horizontal axis here on the bottom on you. On this scale, on this way of plotting it, 0.2 here, that's when all of these curves are sort of merging together, is about a third of a Fermi over C. And by the time we hit 0.5, it's still less than a Fermi over C. Up here, we're sitting at roughly 2 Fermi over C. So, so that's nice. What we were able to show in this case was that there's what's called a forward attractor for the system, where I can start at a fixed initialization time, vary the anisotropy, and I see that they all converge to one curve. Again, losing memory of what happened before. The other way, as I alluded to earlier in the talk, that you can extract the attractors, instead of starting with a fixed time and varying anisotropy, you can start with some fixed anisotropy and then vary the time. So that's this curve. Here we chose to just start with a perfectly isotropic initial condition and then reduced the time by I believe factors of 2 between each of these different curves. And once again, within our numerical accuracy, you can see that there's an attractor building up. Now, this is again, in this case of M01, which was what everybody had looked at before. And what we wanted to do was enlarge it to this giant table. So now there's many curves in these plots. Let's first try to look at them in an entirety. So in this plot, I've combined both the forward attractors and the backwards attractors. So everything is combined, and both types of initial conditions, RS and CGC. And if you move your head back from the screen and squint a little bit, you'll see that you can clearly see these lines along which things are piling up as a function of this rescaled time. In these plots, we've also tried to include attractors or hydrodynamic. In this case, it's the RTA attractor, is this purple line here. This is the ahydro attractor as this red dotted dash line. And these are the viscous hydro results that I get from solving the viscous hydro attractor equations and plugging it into some linearized F plus delta F type formula. So, and if we again go back to the big plot, we see that in all cases, once again, ahydro seems to do better. Now, again, I think that just fundamentally comes back to the fact that these moments can't go negative in ahydro, and that's simply why it does better. It also resums the inverse Reynolds number. All right, so, but when you look at all this together, you start to think, well, maybe what we were saying about hydrodynamization was just one small part of a much bigger picture. And so I like to say that hydro is actually the tip of a much larger iceberg, where we're seeing thermalization, kind of full quote unquote pseudo thermalization in QCD. It's still not in equilibrium, but there is a loss of memory of the initial conditions that happens very rapidly, and this is very, very interesting. Now, of course, the practical question for many people when a few people started working on this attractor business was, well, what can I use this for practically for heavy ion phenomenology? And as I tried to advertise in the beginning of the talk, I believe that we can use this to provide some constraint on the form of F plus delta F, essentially. So in this paper, as our second part, what we wanted to do was take now those attractor solutions that we got and then try to assess different freeze-out prescriptions. So the first one that we considered was the standard quadratic approximation, which emerges in RTA, momentum-independent relaxation time, momentum diffusion theory, scalar field theory, you name it. This is the form that emerges as the leading order correction, where this pi bar here is just the shear viscous correction divided by the energy density. This thing is anisotropic in momentum space, as you can see. As it has to be. Now, the next possibility that we considered came from a paper from 2009 by Dussling, Moore, and Tini, in which they showed, at least for high momentum modes, that if you take into account LPM suppression, that this quadratic form can be modified to something where the power isn't 2 here. I believe in their paper it was more like 1.388, and here we just said, well, what happens if we choose 3 halves here? And then the final one is to just use the ahydro form. So in all 3 of these cases, what we're going to do is we're going to take the result for M01 bar, and we're going to fit the free parameter, in this case, pi bar in the first 2 cases, and in the last case, Cassi, so that we exactly reproduce M01. Once we've exactly reproduced the longitudinal pressure, and we had already, they all agree on the energy density, we basically filled out the energy momentum tensor. So we've matched the theories. And now once we've extracted that pi or Cassi, we then want to use these forms for delta F to make predictions for the higher moments. So here are 3 panels from our study. I don't show M01 here. I'll show it on the next slide, but M01 is the one we match on, so it always works. And then once again, you see that in this case, again, ahydro seems to work much better in describing even these higher moments of the distribution function. Now, of course, we can generate lots of plots of this kind. Here is that M01 that I said. Now, in this case, they all agreed by construction, because we what we did for this case was just fix pi and or Cassie, so that all of these curves, these are actually individual runs from the code, were always reproduced. And then the curves in the rest of the panels are the predictions of the various schemes. And as you can see, this tells us that maybe we should try to use this ahydro form for freeze out instead of these other ones, if we're super far from freeze out, or if we wanted to describe more accurately things that are going on in the hard part of the spectra. So as my last slide, officially, I want to advertise that DECRA has been hard at work. We've teamed up with Alexis Mazalauskas, and we're now using his code that includes quark degrees of freedom as well. And using that, we can also extract these scaled moments. Now, these are the moments summing over both quark and gluon degrees of freedom. We can separately look at the ones that only involve the gluons or the quarks, but in this case, this is the summed one. Again, as a function of this rescaled time, and this sort of is suggestive, right, that you can also have this pullback attractor in this case. Now, these are preliminary results. You don't see these lines completely collapsing at late times, and that's because we're using a relatively small lattice, in particular with respect to the number of points in the theta direction. So hopefully, as we jack up that number, at least that's what happened in the gluon case, these curves start to collapse more and more. All right, so first for the conclusion. So the first part of the story is that there seems to be this attractor for low order moments, like the pressures, and it's well approximated by hydro, but the system's not in equilibrium. So that made a kind of sea change in heavy ion physics, where we had to replace this idea of thermalization of the QTP by something called hydrodynamisation. And with the implication being that we don't have to be in perfect thermal equilibrium to have hydro work. But what we found by looking at the higher order moments was that these RTA and EKT higher order moments are poorly described by standard viscous hydro. Now, that's not a surprise, because hydro is intended to be used for low order moments, and one expects it eventually to break, but we want to know which one breaks the best, I guess. So, and because of this, what emerges from EKT, although it contains hydrodynamisation in the sense that M01 and the other low order moments are described by hydro, it looks more powerful than that, and I'm going to call it pseudo thermalization, just to get the hydro out of the name. Something else is going on here that's causing all moments of the one particle distribution function to have very strong attractor-like behavior. There's a loss of memory, but the system is not in perfect thermal equilibrium. The other thing that we established in the PRL was just the existence of this attractor. As I showed you in the talk, we looked at two different types of initial conditions. You might consider looking at other types of initial conditions. We showed that there is a pullback attractor and that collapse occurs in all moments. And then finally, I discussed how you can use this to assess different freeze-out prescriptions. So this is being turned into something practical. I have a student in Kent State. Her name is Chen Du. She came from Wuhan and is staying with us for a couple of years. And together with her and Chun Shen, we are in the process of writing a module to do ahydro type freeze out in music. And results are coming soon. Thanks for your time.
Thanks, Mike. So after this very new set of exciting results, we have a lot of questions. So maybe I would ask Kirill to ask his question directly to Mike.
Hi, thank you for the great talk, Mike. So my first question was basically to get some interpretation. On slide 8, what are the initial conditions? So does the bad behavior at those corners get better once one starts closer to the hydro attractor?
Sorry, I somehow lost the window in trying to look at you. Where's my slides? Okay. Sorry, you wanted slide 8? So here. Kirill,
So what kind of initial conditions do you have there, basically?
Yeah, so here the initial conditions were Monte Carlo Glauber, and we only initialized the energy density, and we initialized the shear terms to 0 and the bulk to 0. So we started it as a perfectly isotropic quark-gluon plasma here at time is equal to 0, but with geometrical fluctuations in space.
And my question was basically, does it improve, or is it a possibility? Is there any possibility to get closer to the hydro attractor for initializing this simulation?
Yeah, I mean, of course, you could try to initialize on this line with something that was closer to the attractor, but I don't think that's physically what you want to do, because, I mean, all of these things are going to relax to the attractor. That's the kind of blue zone. You can't see it here, but what if you start with 3 different fluctuating initial conditions, you're going to enter this blue zone similarly, right? You can initialize on the attractor by essentially tuning the initial shear correction, and then you would see just a sort of more continuous flow, right? Instead of having the fluctuations that collapse to the attractor, it would just sort of go up, you know? I hope that answers your question.
Yes, thanks, sorry.
Kirill, you had another question, right?
I have a couple of questions, but I think I was not the next one with a question. But
no, it's fine.
okay.
You can.
All right.
Continue,
Okay.
Please. Yeah.
So maybe I will just go. I mean, I just go to my third question actually. So how are the different parts of the hydro attractor, of the non-equilibrium hydro attractor, of the effective kinetic theory connected to the stages of bottom up? So is, for instance, there are those different stages. In the first stage, for instance, is the classical attractor there. Is kind of behavior visible there, or what about the radiational breakup and so on? So in the evolution, is it visible there?
Yeah, it was hard for us to. We were trying to address the same question, you know, before the paper came out. Like, can we see some indication? And all of that is happening in this turnaround region. So all of this early time stuff that you see here that I'm pointing out, that's very well described by the free streaming evolution. And then all of the interesting, you know, bottom up kind of physics is happening in this little turnaround point. And I would guess that you can extract, you know, the presence of these, you know, soft radiation processes in the way that these curves approach the attractor. But we did not do that.
Thank you. Sorry, maybe the next question can be got by somebody else. That's why I'm just hanging.
Yeah, the next question was by Ayan. So Ayan, please go ahead.
Hi, Mike. Thanks for the nice talk. I wanted to ask something. So this is actually regarding, I think, your slide 24. So, or even this slide, actually. So essentially, your statement was that the higher moments somehow approach the attractor faster. So what if you start from some initial condition where one of the higher moment is very far away from that attractor value, whereas the longitudinal pressure is close to that attractor value, say. And this is the first question. And the second question is essentially, I want to understand, so normally that attractor is sort of well behaved at early time. So what does this entire distribution function tends to at, is there some way you can talk about it? Maybe the question is to Knife. So this is basically the two questions.
All right, so yeah, I was careful to say that, at least from what I've been able to look at, RTA is they go to the attractor faster for the higher moments. I don't know if the same can be said for these guys. I'd say it's about the same. It doesn't look similar. But if we look at RTA, then in fact they do approach the attractor earlier for the higher moments. And what was your question in regard to that?
Yeah, what happens, you start from an initial condition where one of the high moment is far away from the attractor value, but the longitudinal pressure is very close to that attractor value. Some atypical initial condition.
Yeah, I didn't look at any atypical initial conditions. So I basically, whatever was here was the seed for this. Now, if you notice from these plots, if I go up to the topmost line here, that's a relatively small deviation from equilibrium, but that's not even on the scale here. So it's actually a quite large deviation in this highest moment that I show you. And we went down to 4.4, and so that would have an even larger. So these curves, I can give you a situation where the longitudinal pressure is very close to 1, not necessarily 1, but these are very far from 1. That naturally happens. But I didn't try tuning, some specific initial distribution function that would give me a super large one. That's an interesting question. Now, I think, of course, you can always tune, you can always find an initial condition that's sick enough that it will take forever to relax it, right?
Yeah. Okay, so then typically the attractor is well behaved as tau is equal to 0. So some kind of dimensionless characterization of moments should be well behaved, or you can somehow talk up some kind of a distribution function on the attractor at tau goes to 0 limit. Yes,
in particular in RTA, because there was an exact solution and I could beat it to death. You can, I don't show super early times here, but you can extend this black line all the way back to tau 0, and you can extend this plot all the way back to tau 0. So yeah, the answer is yes. Now in QCD, it's suggestive that because we have this pullback attractor, the same thing happens. That if I can pull these all back to earlier and earlier times, then the fact that they all collapse here is telling me that I can extend this back to super early times. And at some point you can match the attractor smoothly to the plasma then? Well, this is, in this EKT way of doing things, it's supposed to match to the plasma because they've already taken into account that the occupation numbers can be non-perturbatively large. That's built into the code already. So it should smoothly match onto plasma after the plasma pressure is positive. Thank you.
Then next question is by Ashutosh. Ashutosh, could you please unmute and ask the question?
Hi, Mike. So my question is related to Ayan's question actually. So I wanted to ask, instead of using this Romaske Strickland form of initial condition and changing the anisotropy parameter, if you use some arbitrary initial condition, what will happen? Do you see the same attractor?
Yeah, we didn't look at an arbitrary one. We just looked at another possibility, which was CGC. And there, the shape of the distribution function is completely different. It's a Gaussian, essentially, in this way with some scale. It is distorted like RS, but it definitely doesn't have a thermal form like RS does. So in the future, one can imagine enlarging this class that we looked at, but it was enough work just to do 2 already.
But one can put any arbitrary random number for the movement in initial condition, right? I mean, given it is positive definite and
Yes, so you can put in whatever distribution function you like. Yes, that's correct.
want. Okay.
Within the approximation scheme.
Yes, yes. Thank you.
No problem.
Yeah, the next question was Zoran. Please go ahead.
Yeah, so again, a related question to this issue of initial conditions. So it's very impressive to see how well this ahydro form works for essentially both of these. But I'm wondering whether this relies on the fact that in both of these initial conditions you essentially have a single scale where your energy density sits, right?
Mm-hmm.
So I'm wondering, I don't know if you've looked at this or whether my intuition is wrong, but typically if I were to actually do the CGC calculation, I would get a power law tail, right? Which essentially at some point describes your jet production and so forth, mm-hmm. right? And these are definitely modes which relax on the different on different time scales. So to me, it seems that the single scale assumption is somehow necessary to get this behavior. Or
I believe it's necessary, but I don't know if it's sufficient. Mm-hmm. Because of course, if we have more than one scale, it starts to become, as I mentioned earlier, right? What do you use for tau r down here? So if you start different scales, even the whole concept of the attractor becomes a little, at least in the kinetic framework, there are some ambiguities that pop up, let's say.
Yeah, because I think this is actually, in principle, I think this is an important difference between QCD and RTA, that in principle, I think in QCD, you can in principle cook up something which doesn't necessarily just equilibrate in one unit of kinetic equilibration, mm-hmm. right? If you have sufficiently high energy jets or something like this. Right. So it would be, so this goes into the same thing. I think it would be very interesting to kind of enlarge this search space a little bit and see.
Yeah, I agree, but we have people have to get PhDs and.
Yeah, sure.
No,
I use the same things.
One of the things that we're looking at is, of course, we could also look at strongly under-occupied initial conditions, right? And which are not here.
To me, the most natural
that would be
thing
more
to do
like your jet
actually
picture,
just.
Right?
Actually, just use the KT factorization formula for the initial gluon spectrum, right?
Right.
That's in principle not that difficult to do, right? But we haven't done it either.
Mm-hmm.
Yeah, the next question is Paul. Paul, could you please unmute yourself and ask?
Hi, Mike. Thanks for the talk.
Hi, Paul. Nice to see you again.
I had a comment and a question. The comment is on the exponential form that you said was implemented in Sonic in the introduction. I wanted to comment that this exponential form for Bjorken is the same as the ahydro form, simply because there's not much freedom left. So it's the same exponential form.
Yeah.
And the question that I have because of this is, so basically in Sonic, this exponential form is implemented in a fully 2+1 dimensional way. So are you re-implementing this now in your advertised work with Chun on page 42? Or what is it that you have in mind? What's different?
Yeah, so what's different is that I guess what you guys did in the past is, right, you took f plus delta f and then you rewrote that as an exponential and got a kind of effective anisotropy parameter out of that. What we're doing differently is we're going cell by cell, and then we fit the anisotropy matrix in this case and a scale to exactly reproduce T mu nu in the local reference frame. And then we sample from now this anisotropic F.
So that's basically what's implemented in Sonic. Is the T mu nu, at least for the case without bulk viscosity, is fully reproduced, and we sample from this distribution function cell by cell.
Okay. Yeah, I'm happy to reproduce something you've done in the past. I think it's the right thing to do in the case that you have these large deviations from equilibrium. Now, in the future, we don't have to do this conversion because we would use A hydro for the entire evolution, and then we just take the anisotropy parameters on the freeze out hydro surface and sample it directly. But that would be sort of like applying this trick, from the beginning.
Okay, thanks.
Thanks, Paul.
Yeah, and Kirill has one more question to ask to you.
So this was the one question I kind of skipped. So on slide 26, basically you have two contributions, two components, right? I don't see the slides at the moment, but anyways.
I put them back up.
Okay.
Sorry.
So it seems to be something like two coupled fluids. And when you think about the EKT attractor, or differently, when you think about the bottom-up scenario, then you also have the soft sector, which is more or less isotropic, and this is basically what EKT also uses. It uses something isotropically screened, and some hard, very anisotropic sector. And then there was also this two-fluid model in ADS, where we had this one with a very nice talk today about heard about that. So is all of that already the reason why we see so similar behavior between RTA, between kinetic theory, although RTA is much easier and simpler than EKT, for instance, and may this already be some on a qualitative way the reason for that?
Yeah, I think the qualitative similarities that you see between, let's just look at the bottom because it's easier on the eyes, between this and what you would expect from bottom up, yeah, it's there, right? I mean, except for the detailed physics is not done correctly because it's RTA. But what we see is that there's always this, population of hard particles that are becoming extremely anisotropic, and then they eventually do scatter and go away. And during this time, it's building this guy up. Now in QCD, this buildup is not done through RTA, right? It's done through, as you know, the radiative processes. But qualitatively, it looks the same, right? You have some subset of hard particles. They're highly anisotropic. They disappear as a function of time because they do scatter eventually, and then you get to the thermal or near thermal equilibrium form.
So may this be kind of one of the key explanations why all those different attractors, hydrodynamic or even non-equilibrium attractors, are so similar between all those different theories?
Yeah, I think that, underlying all of this, right, is that in all of them, at least the ones that we know exactly in kinetic theory, you basically have to go to the free streaming limit on the left, and you have to go to the hydro limit on the right of the plot, right? And now what happens in between, that's up to the specific model.
Okay, thank you.
Yeah.
Okay, I see no further questions. So thank you, Mike, for this very exciting talk.